Welcome to Water Science for Everyone.
Have you ever dug a hole in the ground and noticed water beginning to fill it up? That moment, where the dry earth transforms into wet ground, marks something incredibly fundamental about our planet's hidden water systems. That precise level, where the ground becomes fully saturated with water, is exactly how the water table is defined within an aquifer. It represents the upper boundary of the zone of saturation, a critical point where all the tiny pores and cracks in the subsurface material are completely filled with water. To truly understand this, let us visualize the layers beneath our feet. Directly below the surface lies the unsaturated zone, also known as the vadose zone. In this area, the pore spaces within the soil and rock contain both air and water. However, as you delve deeper, you eventually reach a specific depth where all those spaces are exclusively filled with water, existing under hydrostatic pressure. This region is called the saturated zone or phreatic zone. The very top of this saturated zone is what we refer to as the water table, essentially marking the atmospheric pressure boundary. Its presence and depth are fundamentally governed by the porosity and permeability of the surrounding geological formations, which dictate how effectively water can infiltrate and accumulate. Grasping this concept is absolutely essential for the responsible management of our invaluable groundwater resources. We can directly determine the depth of the water table by installing observation wells, often called piezometers. In these specialized wells, the water level will naturally rise to perfectly match the elevation of the water table in an unconfined aquifer. This provides a direct, measurable insight, which is then used to accurately map groundwater flow directions and depths across an entire region, directly informing crucial decisions about well placement and sustainable water withdrawal rates. It is also important to understand the nuanced distinction between the water table in an unconfined aquifer and the potentiometric surface found in a confined aquifer. While the water table is a tangible physical boundary with air above it, the potentiometric surface in a confined aquifer signifies the hypothetical level to which water would ascend in a well due to the immense pressure exerted by the overlying confining layers. Another fascinating detail is the capillary fringe, a thin zone directly above the water table where water is drawn upwards through capillary action, creating a partially saturated layer. This shows that the transition from unsaturated to fully saturated is not always a sharp, distinct line. Ultimately, a clear definition of the water table provides the foundational knowledge for all of hydrogeology. It is not a fixed or static characteristic but, rather a highly dynamic boundary that constantly fluctuates in response to factors like rainfall, periods of drought, and significant human activities such as groundwater pumping. Recognizing its vital role as the crucial interface between the unsaturated and saturated zones helps us to deeply understand the availability, movement, and long-term sustainable management of groundwater, which remains absolutely vital for supporting both ecosystems and human consumption.
If you love learning about water, like, subscribe, and keep exploring with us.